I have here another problem involving a mixture of ideal gases. So, let us consider an ideal gas mixture which has 1 kilomole of hydrogen and 1 kilomole of nitrogen. Find the mass fractions and mole fractions and also R and Cv and Cp. So, let us write that down. What we would call as an equimolar mixture, equal number of moles of hydrogen and nitrogen. So, what we are asked to find out here is the mass fractions and the mole fractions and R, Cp, Cv. So, we are looking for X, Y, R, Cp, Cv, and then we are going to use these data to find out what happens when this mixture undergoes some process. So, X for hydrogen is essentially number of moles of hydrogen divided by number of moles of hydrogen plus number of moles of nitrogen. That is the definition of the mole fraction. So, that is 1 divided by 1 plus 1, which is 0.5. Similarly, X of nitrogen, we can do the same thing, or we can say 1 minus X of hydrogen, and that is also equal to 0.5, because we have the requirement that sum of all mole fractions should be 1. We can find out the molecular weight of the mixture. This is given as sigma of xi into molecular weight of I. So, I have 0.5 into molecular weight of hydrogen, which is 2, plus 0.5, which is this, into molecular weight of nitrogen, which is 28. So, it is essentially 1 plus 14, which is 15 kg per kilomole. That is the molecular weight of the mixture. I need to find out the mass fractions. So, the mass fraction of hydrogen is essentially, so we have mass fraction is so that is 0.5 into 2 divided by 15, and so this is actually 2 into, okay, it's not going to be easy anyway, 0.06. So, I have the mass fractions and the mole fractions. So, this part I found. I need to find out the gas constant for the mixture. So, I am asked to find out the gas constant for this specific gas constant for the mixture. Again, there are various ways in which I can do this. I can either find out the individual gas constants of the gases and then find out the summation of them, or I can find out the gas constant using the mixture molecular weight. Any of them should be okay. So, the gas constant R, the specific gas constant, is defined in this fashion. It has units, if I take it the specific gas constant, it has units of say joule per kg Kelvin. So, it is something per kg. So, what I can do is I can find out R of the mixture as sigma of yi into Ri. I can do that, or I can just do this. I can, so where if I am doing this, then individual components I will find like this, but by the same formula I can also find out R of the mixture is R bar by molecular weight of the mixture. I can do it in this way as well. This is possibly easier to do. So, A314.5 divided by 15. So, that is something I can do. This will give me 554.3 joule per kg Kelvin. I think there's a 9 over here which got missed out. Is that right? So, we have this, but none of this changes. That was a 9 which got missed out there, but we still have this. So, we are asked to find out Cp and Cv of the mixture. So, here we see that we can do it in different ways. So, if we have Cp and Cv in this fashion, they have units of say joule per kg Kelvin. So, Cp of the mixture would be summation of Yi into Cpi. Similarly, for Cv. So, I know Yi's, I have to find out Cp of the ith species, and then I can find out this. Similarly, I can find Cv in a similar fashion. What I can also do is, for each of this, I can find out Cp on a molar basis for the mixture, which will be sigma of xi into the molar Cp, because if I take molar Cp and Cv, this has units of joule per kilomole Kelvin, which means I can add them in this fashion. I can do this as well. And then after doing this, I can convert it back into this by using the molecular weight of the mixture. So, I can do it in either of these ways. So, what I am going to do over here is find out Cp and Cv individually for the gases first. So, Cp is given as gamma into R by gamma minus 1, and Cv is given as R by gamma minus 1. Now, I need to find out these for each of the species. So, let me maybe just divide this here. I can also find those in different ways. So, if I use R, which is the gas constant, R has units of joule per kg Kelvin and Cp has units of joule per kg Kelvin. If I use R bar, which has units of joule per kilomole Kelvin, I will get Cp bar and Cv bar. So, I can do it in either way I want. So, if I want to use R here, I need to find R, which is R bar by m. So, Cp for say hydrogen would be gamma of hydrogen. So, hydrogen is a diatomic molecule. So, gamma of hydrogen would be 1.4 into 8314.5 divided by molecular weight of hydrogen is 2. So, this is gamma, this is R of hydrogen, which is this, divided by 1.4 minus 1. Similarly, I can find out Cv for hydrogen as well, or I can find R for hydrogen, which is 8314.5 divided by molecular weight, which is 2, and then I can add these. So, this is 4157.25. So, Cp is R into gamma divided by gamma minus 1, which is 14,550. Cv is R by gamma minus 1, but we also have that Cp minus Cv is equal to R. So, Cv is essentially Cp minus R. Which is 10,393. So, I have these values for hydrogen. I need to similarly find out values for nitrogen, which is our second species over here. So, I need to find out for nitrogen. So, Cp for nitrogen. So, let me first find out R. R nitrogen is R bar divided by molecular weight. R bar is 8314.5, molecular weight is 28. So, if I divide those, I get the value as very close to 297. I get 296.9. I am going to round it off to 297. So, I can find Cp of nitrogen, which is gamma, or let me find out Cv of nitrogen first. This is R by gamma minus 1. R is this, gamma is 1.4, it is a diatomic gas. So, I have 297 divided by 0.4, which is 742.5 joules per kg Kelvin. And Cp is gamma into R by gamma minus 1, or essentially Cv plus R. So, this plus this, which is about 1040 joule per kg Kelvin. So, now I can use any of these formulae. I found out these in terms of kg basis. So, I will use this formula. What I would suggest to you is find out these on a mole basis and use the other formula. You could also do that. So, because if I wanted to find on a molar basis, I would not divide this R. So, what I would have here is Cp bar is gamma R bar by gamma minus 1. So, R bar is known, it is 8314.5. I know these values. Sorry. This is actually in some sense easier to do because gamma is the same for these two gases. Both are diatomic gases. So, Cp and Cv on a molar basis are the same for these, for both hydrogen and nitrogen. So, if I just did this calculation for hydrogen or nitrogen, they would be the same because R bar is the same, gamma is the same, and then I would find them using this. So, maybe I will do both of them just to show you that, to convince you that they are the same, but I am going to first do this. So, here I have Yi for hydrogen is 0.066 into Cpi is 14,550 plus 0.934 into 1040, which gives me a Cp for the mixture. Sorry. This gives me a value of 1931 joule per kg Kelvin. If I was to instead do this, I would get Cp bar as 1.4 divided by 0.4 into 8314.5, which would have been 29,000 each for both the gases. So, this in terms of mole fractions, now it would be 0.5 into this, because the mole fractions are equal, plus 0.5 into this, which would essentially give me the value as this. Sorry. Now, the way to find out Cp mix from Cp bar mix, this is per kilomole. I want something per kg, so I need to divide it by something which has units of kg per kilomole. So, the same way over here, if I want R, I divide R bar by M. Here I would divide this by the mixture molecular weight. So, this would be 29,100 divided by the mixture molecular weight, which we found as 15. Which will again give us, because of approximations I have done in each of the stages, I get a value of about 1940 in this way. If you took sufficient decimal points in all of them, you should get the same thing in both the ways. What I have done here is I have cut off after the second digit over here, and in many of the other places here, I have rounded off. So, I get slightly different values, but essentially you should get the same. If you took into account enough digits, you should get the same. So, both these are equivalent ways of doing it. So, what I can also do is find CV of the mixture, which is Cp of the mixture minus R of the mixture. So, I have Cp, one of this value. I had R for the mixture as 554.3. which is about 1385. I can also find gamma of the mixture, which is Cp of the mixture divided by Cv of the mixture, which is also equal to Cp bar divided by Cv bar of the mixture. This keeps going off. So, this is my value of Cv. So, 1 by Cv into 1940 gives me a gamma of 1.39999, which is essentially 1.4. In this particular case, I need not have found the gamma this way, because I know that both the gases are diatomic. So, the mixture will also remain diatomic. But what you should keep in mind is, in general, that is not true. If I was mixing, for example, helium and hydrogen or helium and nitrogen, the value of gamma would change depending on what is the fraction of helium and nitrogen. If I had a monatomic and a diatomic, or a monatomic and a triatomic, or a diatomic and a triatomic, etc., the gamma values would depend on the composition of the mixture. So, this is how we would find it out in those cases. So, after finding out this, we have now the Cp values, we have the Cv values, we have the gas constant. What we are asked to do is to find out delta U, delta H, Q and W if this mixture is heated at constant pressure from 300 Kelvin to 400 Kelvin. So, we now have a constant pressure process. We are asked to find out the change in internal energy, change in enthalpy, the work and the heat transferred. This is a constant pressure process. So, P is constant. So, what we know is that the heat transferred is given by m into Cp into delta T. This is Cp of the mixture. The mass we had over here, we had 1 kilomole each of these. So, we can find out the mass using the ideal gas law. So, the total number of moles is 2 kilomoles. So, we have PV is nRT, or we can have where R nR bar T, or we can use it as PV is mRT and try to find out what is the mass that we can do. What we also have is we also need to find out delta H. This is a constant pressure process. So, this is going to be equal to m into delta H. So, that is taken care of. We are asked to find out delta U. If we take this as a mixture of ideal gases, this is also equal to m into Cv into delta T. We have already found out Cv of the mixture. So, we can find out the delta T is known, it is 100 degrees. If we know m, we know this. If we do not know m, we know all of these on a per kg basis. So, we can find out, for example, Q by m. delta U by M and so on. What we are also asked to find out is work. The work is it's a constant pressure process, so it is P dV. And what we also know is from the first law, Q is delta U plus W. So Q minus delta U would also give me W. So I can find out these values of these things as well. So I have run out of space, so I am going to maybe break for a moment. So I had this and I had this. So I know the molecular weight of hydrogen is essentially 2 kg per kilomole. So if I have 1 kilomole, then the weight is, or the mass is 2 kg. So what I have is that the mass of hydrogen is essentially this into this, which is 2 kg. Mass of nitrogen, I know the molecular weight of nitrogen is 28 kg per kilomole. So mass of nitrogen is essentially N times M, which is 28 kg. So the total mass of the mixture is 28 plus 2, which is 30 kg. So that I know. So now I know the mass of the mixture, I know Cp of the mixture, and I know delta T of this mixture. So this is 30 kg into Cp of the mixture is 1940 joule per kg Kelvin into delta T is 100 Kelvin, which gives me some value. This is 30 into Cv is 1385 into 100, and this is this minus this. This is 5.8 megajoule. This is 4.1 megajoule, and this essentially is 1.7 megajoule. So that's essentially what we get for this problem. So we see that we can do this in several ways. So for example, even here, I could have found them all on a molar basis and then converted into a mass basis and so on. So there are many ways in which we can do this. All of them should give you the same answer as long as you are doing it consistently and correctly. Because I want to quickly do this here, I have been rounding off a lot of those numbers. If you take, I would generally recommend at least taking 2 or 3 digits after the decimal, at least 2 digits. In many cases, I have, for example, rounded off to less than a digit. So if you didn't do all of that, you would get the same answer in all of the ways.